This question is about the gas laws, specifically Charles' law, and it starts by asking us to convert Kelvin temperature to Celsius. So just a reminder that when we want to convert Celsius to Kelvin, we have to add 273. When we're going from C to K, alphabetically we're going up, so we add 273. If we're going from Kelvin to C, that means we're going backwards in the alphabet, therefore we have to subtract 273. So in this case, we need to subtract because it's Kelvin to Celsius, so 4.2 minus 273, it will give us the temperature of minus 268.8. The second question is asking us to describe the arrangement and the motion of the molecules when the helium becomes from liquid to gas. So I've added this diagram just to remind you about the arrangement and the motion of the particles in the three states of matter. In solids, the particles, they don't move, they just vibrate. But then when the solid melts or when it becomes gas, then the particles, they can actually move. And the arrangement, as you can see, in solids, they're very close to each other. But then when it becomes liquid, they're kind of moving slightly apart. There's still bonds, there's still forces holding the particles together, but then when it becomes gas, the particles, they move further apart. There's no bonds anymore. The forces they have been overcome. And these are the things we need to mention in our answer. So there's 2 points for this question. 1 point will go if you say something about the arrangement, and the second will go if you say something about the motion. So since I'm heating the liquid helium up in order to boil it, that means I'm providing thermal energy. This thermal energy becomes kinetic energy in the particles, and therefore the particles, the molecules, they move faster. And as we already discussed, the molecules will move further apart when it comes to gases. And the forces, they're not there anymore, therefore the molecules, they move randomly and freely. The next question is asking us to sketch a graph to show the relation between the average kinetic energy and the temperature in Kelvin. So when it's asking us to sketch a graph, that means there's no numbers or units or anything involved. It's just to show the relation between the two by drawing a graph or a curve or whatever the relation is. If it's asking us to plot a graph, then it should provide us with data, with numbers, so we can put the points, we decide the scale, and so on. So in that case, the relation between the kinetic energy and the Kelvin temperature is, as you can see here, it goes through the origin. And why it's happening this? Remember that when we're boiling something, we're providing heat, therefore that heat turns into kinetic energy. So as I increase the temperature, I have more kinetic energy, and this relation is kind of a proportional relation. As one increases, the other one increases in a linear way. And the other way around, if I'm cooling down something, that means I'm removing the kinetic energy from the particles. And as I keep removing the kinetic energy, at some point the kinetic energy will run out, and this is the equivalent of the zero temperature in Kelvin. This is what we call the absolute zero. There's no lower temperature than that because I have already removed all the kinetic energy from the particles. So therefore this line should go through the origin. If the question was asking us to sketch a graph of the average kinetic energy with the temperature in Celsius, then the graph should have looked like that. So we have negative values for temperature in Celsius. The lowest possible value for Celsius will be minus 273, and then we have the same pattern, the same line, but it's going back on the negative x-axis until it reaches minus 273. So the next question is asking us to describe an investigation to see the relation between the temperature and the volume. So I have added a few more diagrams in this question, but the original diagram is just that, and I will explain it a bit. So we have a narrow glass tube. This is sometimes called a capillary tube. It's a very, very thin tube with a tiny hole in the middle. And what do? We just put a drop of a liquid. Usually we use oil or sulfuric acid. And what happens once I put that liquid? The liquid will start moving down on that tube, and at some point it will stop at a specific point, as you can see there on the diagram. Now, why it stops there? This is because inside this part we have trapped air. And what happens when air is trapped? The molecules are moving randomly and freely in that tube, and then the molecules, they hit the walls of the container, and those collisions with the wall, it's causing a pressure. Now that means there's a pressure pointing upwards, pushing the liquid up, but then at the same time, at the top part of the tube, it's an open tube, therefore air can get inside the tube, and therefore the pressure on the top is actually equal to the atmospheric pressure. Now, when pressure A and pressure B are equal, then the liquid will stop moving. Now, what happens if I increase the temperature of that trapped air? If I increase the temperature, that means I'm giving the particles more kinetic energy, therefore they're moving faster, they are colliding with the walls more frequently, and they're doing this with kind of more force, and that will increase the pressure on the trapped air. Now, if the pressure at the bottom, if pressure B becomes more, then that drop of liquid will start moving up. Right, so the liquid will move up, and what will be the effect of that? The volume here will become bigger, and that will kind of decrease the pressure. When is the liquid going to stop moving? Again, when the pressure from the bottom, it will be equal with the pressure from the top, the atmospheric pressure. When these pressures are in equilibrium, then it will stop moving. And this is what I'm trying to do in this investigation. Now, how do I do it in reality? So this is how the apparatus looks like. I have the capillary tube here, and then the thermometer here to measure the temperature. And I'm placing this in a beaker full of water. Now, I can do this in two different ways. I can use room temperature water and then use a heater to heat the water up. Therefore, the temperature will change, and I will see changes in the length of that column of air as the drop of the oil or the acid or whatever will start moving up or down. Or I can start with hot water and then allowing the hot water to cool down, and then I'll get changes in the length of the air column. The whole idea here is to get multiple measurements. So for different temperatures, I will have different lengths. Let's have a look at the answer. So as I think we have mentioned most of these things. So we're going to need the thermometer to measure the temperature. We're going to need a ruler to measure the length of the tube. Now the question will be, I'm trying to investigate the temperature and the volume, but here I've said that I'm measuring the length, so it's the volume that I need to measure. Is that important? Now, as the length increases, then the volume increases as well. So it's the same relation. So the same relation temperature will have with volume is the same relation that we'll have with the length. So by measuring the length will be enough to see the relation. If, however, I want to measure the volume, then I need to add a few more, I need to do some more measurements. I need to find the diameter of the tube in order to find the cross-sectional area, and once I know the cross-sectional area, if I multiply with the length, I will get the volume. So this is a bit of maths. But as I said, length only will give me the relation I want to see. And we need to use a beaker with water, either hot to let it cool or room temperature with a heater to heat it up. Then, as I mentioned, we have to take a range of values on changing temperature and the equivalent length of the air column or the volume. In every investigation, we repeat it. We repeat every investigation and we find the average of our results. The reason we're doing this is to improve the reliability so we can trust our results. And then, of course, every time we collect data and we get values and results, then we present them. So we have to draw a graph to show the relation between the quantities that I'm measuring, the temperature and the volume or the length. And since this is about Charle's law, which is V1 over T1 equals V2 over T2. The temperature in this case, it has to be in Kelvin. And remember that Charles' law, in order for Charles' law to be valid, the pressure has to be constant.